My name is Toby. I'm the project lead for AI Startup Rising. And AI Startup Rising is a Germany by BMWK, Bundesministerium für Wirtschaft und Klima, funded project inside of hessian.AI. We are most of the time supporting research-based startups, but not only. And we are currently setting up a quite variety of different formats, like the AI Academy that you can see today. We have the Open Idea competition running until the 22nd of May. So maybe this talk by Harini is inspiring you with nice ideas that you can hand in later in the idea competition. And also, as a reminder, every Monday currently we have our masterclasses with inspirational talks of different kinds of founders and also some coaching sessions. Afterwards, today, Harini is joining from Omdena, and Harini is Vice President of Projects at Omdena. She joined as a junior machine learning engineer in 2020 and was quickly promoted to mentor. And if I'm informed correctly, she's currently pursuing a master's in computer science at the University in California and specializing in deep learning, applied machine learning, NLP, and differential privacy, and many more. And because Harini is so eager to solve real-world problems with the help of data and best fit models, she joined Omdena, a global AI community with impact-driven organizations to educate, innovate, and deploy AI solutions in the world. And Omdena, by the way, is also having a special prize for the idea competition of hessian.AI and AI Startup Rising, which is a few hours of mentoring and coaching with machine learning engineers for the best and most inspirational ideas. Today, Harini is presenting one of Omdena's projects, that is to help visual impaired people through computer visions. And without further ado, Harini, stage is yours, and pretty excited to hear you talk.
Yeah, thank you very much for the introduction, Tobias, and I'm excited to be here with all of you. I hope you'll find the talk useful. So let me go ahead and share the screen. I hope everybody is able to see my screen. Okay. Yeah. So let me just pause this video while I'm speaking. The project introduction was done with ReNewSenses, a startup with problem statement in mind about helping people with visual impairment to easily use buses through computer vision. So as we know, disability is a very global problem. We have at least So globally, we know that we have at least 2.2 billion people who have a near or a distant vision impairment. And we have at least 1 billion or almost half of the people whose things are yet to be addressed. So some visual impairment problems have been solved and some which has not been solved. And the majority of the population with this vision blindness are actually people over 50 years of age. And we all know that vision loss can affect people of all ages. So to the right side of my slide is a small statistical image of how men and women are being affected in different cases, in different age categories. And as we see, we do know that after 60 years of age, or after 80 years of age, we do have more people who are affected with visual impairment. And here comes the big picture. So most of our projects that we actually do at our organization are concentrated towards sustainable development goals. And it does contribute to any of one of the United Nations sustainable development in terms of if it helps the if it's an economical reason, if it's any social reason. And here, this project is in partnership with ReNewSenses, who came up with this idea because they have the device and they're working towards it. And we as an organization have collaborators who will work on the machine learning perspective of that and try to build a pipeline. So our major project objectives are, we had 3 priorities. As we know, like the project objective was given to assist people with visual impairment in their experience of catching a bus. But we broke down the main problem statement into 3 priorities. That is the first one being that we have to detect if a bus is arriving through real-time object detection. We all know that we have to figure out if the bus is actually arriving or if the bus is standing at a particular point of time. So it is about detecting whether a bus is arriving through real-time object detection. Once the bus has been detected that it is arriving, then we will have to figure the bus plate. Again, given that the specific texts are different in different regions, in European countries, the bus plate would be in different languages, and in Asian countries, the bus plate would be in different language. So that's our second task. And the third one is to determine whether the seat is empty or not empty to assist users in finding an empty seat on the bus using object detection. These are the three main priorities, or the problem statement was actually cut down into these three parts to develop better. And our solution is we built a working model. We created and tested and trained within 8 weeks. So all the slides that we are going to take forward, or all the prompts, the methods or models that we are talking, all of this was actually built in a time of 8 weeks. This is typically 2 months. And then this was very specific to the German countries. So it was very specific to Germany. Hence, we had collected German specific images from videos available on internet. And one of the main approaches that why we actually stand on, we do a lot of projects, is our bottom-up self-managing approach. We will have a product manager, we will have a head of projects who actually oversees that, but keeping these two in mind, we do have a set of collaborators who are self-managed. Nobody is going to tell them as to how to build the product or how to what method we have to use. But in a nutshell, how they are going to do is that they are going to take it up forward by their own ideas as to how they want to build, like from collecting data till the building model till deploying it. It is our collaborators who decide that. The first task is the data collection and annotations. So as we can see over here, we had the first priority task, or the first mini problem statement, was to identify if the buses were incoming or not. So in order to actually identify if the buses are incoming and then identify the bus panels, or even to identify if the seat is available, we wanted to have data collection and annotations. And the main challenges in that is that we do know that we do not have any real-time data sets that are available in the internet. That is, for example, say in many of the cases, most of the data sets that are available are not real time. If we have a temperature data, humidity data, academic data sets, they do not pursue real time data. And in this case too, we did not have any available data. And second of all, we cannot use the already available annotated data for identifying incoming buses, because it's quite difficult, right? Like to identify if a bus is incoming or if it is standing just based on one image which is already annotated. And to detect whether a bus is empty or we have a seat, now that is again a problem because we have a lot of privacy issues. That is, not everybody will be ready to make the image data set available of inside the bus scenes. As we already see, data privacy is a very big concern in these days. So what we did is about the data collection buses is that we had a pipeline which will take care of our data collection task. And the first of its kind was the COCO bus dataset. COCO Annotations is like a very famous dataset that is available for most of the computer vision problems or object detection problems. And now following the COCO bus dataset, which contained 4,000 images, our collaborators, again, this is where our bottom-up approach comes in, where our team of 40 to 50 collaborators went ahead and manually, they went through all the 4,000 images to separate the incoming buses from the non-incoming buses. As we can see, so as we can see over here, this is an incoming bus and this is a non-incoming bus. So we went through all the images manually and tried to separate incoming and not incoming. And then the final set of images was annotated via CVAT, just to identify the panel part. So after identifying if a bus is incoming, we will need to know if that is the right bus our customer or the person who's using the bus has to sit on or not. So in that case, we went ahead and we actually annotated the bus front to see what is the bus label in order to understand that. And this was done using CVAT annotation tool. The second part is about the seats. Again, for the seats, as we already mentioned, not many publicly available data sets are there because we know that it's because of data privacy and other issues. So we went ahead on YouTube and scraped about 27,000 images from the videos. That is, we first downloaded the videos, and from the videos, we generated the images from the videos. And then we removed the duplicate images. And after that, we annotated the empty seats. We only want to consider the empty seats. So we just annotated the empty seats into consideration using CVAT. Now, the summary and future improvements of only the data collection process is quite huge, because we did take a data-centric approach into consideration, but we should also make sure that we will have to add null images to the bus detection dataset. That is, which it should also contain the back of the bus. It should also contain general road images, and then it should also contain the discarded images. Well, we all, to avoid bias, we are only considering the bus panel at the front, and then we are only taking the ones that is needed for us. But it's also necessary to take the null images to the bus detection dataset so that we can make it unbiased dataset. So in some buses, as we know, we do also have the side panels, but in this, we do not take the side panels into consideration, which also we would like to take. And we wanted to like refine the seat image data. So we collect more images and see how we can work on it. And one very important thing that I'd like to mention here is that since we are an international community with about 40 to 50 collaborators from all over the world, from different countries, our major advantage in this project was that collaborators actually went on the streets to take pictures of the buses, and they shared it with us because no images were available, and they went ahead, not, I wouldn't say a step ahead, but multiple steps ahead, and they captured pictures of the buses incoming and then used it for our data collection model. This is an overview of how the modeling should be. And here, as we see, Travis is ReneWsense's our partner's device. So that's the one that is used to communicate with the with our customers. I would call it the person whoever is using the bus. It's the Travis is a device which is actually used to communicate with them. So we have the user, we have the Travis, and that's how this modeling overview. So what we have to see as according to this is that we will detect the object, we detect the text, where we scan the text and understand if that bus is actually useful for us or not, if that is the bus that the user wants to get in. And then we have the bus and the panel detection, and then we have the bus tracking to see if it is incoming or if it is just standing. And then we have the empty seat detection. So after all these three models are ran through, it will be passed on to the Travis model, the Travis device, where it says the available seat has been recognized. And after that, after the incoming bus has been matched, it will interact with Travis. So here we go with our bus detection. And in order for us to understand if a bus is coming or not, it needs a good precision, and most importantly, not to forget, it's a real-time object detection model. So we use the state-of-art object detection model and object tracking mechanism, and the metric that we used to calculate was mean average precision and latency. As we all know, YOLO v4 is one of the models which is very famous for object detection. But just a small change over here, that we actually used a YOLO v4 tiny model. And why we used a YOLO v4 tiny model was because we wanted to ensure that it is compatible with the Travis device. Because Travis device is a mobile embedded device, which does not have it does not have the computational power as our normal virtual machines or normal GPU extensive machines. So we went ahead with YOLO v4 tiny model. The second one is about the bus line detection. And now this is for us to figure out if actually the bus which is incoming is the bus that the user wants to take. And this is to develop a mobile compatible, again, everything over here that has to be developed should be mobile compatible, because at the end, we are going to deploy it on the Travis device, which is a mobile embedded device. So it is a mobile compatible scene text detection and recognition, which is going to extract the German bus panel with the line number and the destination name. This project was like it was built based on the buses in Germany, but in the future it was also meant to be extended to the other countries like Switzerland and Poland, etc. But for the first time, it was built keeping the German buses in mind. So we try to detect the German bus plate, which is there using OCR, optical character recognition model. We check the user input from Travis. So basically, Travis will tell us if the user will let Travis know what kind of bus he's interested in, if he's interested in taking a bus to which location. And based on that, our model will take the OCR, use the OCR model and take the text and understand if this bus is the bus that actually the user is expecting. And this is our modeling, which is of OCR pre and post processing. So as we all know, when we have an image and from that, when we want to take the text of the bus number and the bus name, it would be slightly blurred because we're already working on an image which was captured by a camera. And as we can see here, the color of the whatever the color or the light of the name of the bus could be a bit distorted. So we had to do a bit of pre-processing before actually applying OCR on it, and that includes noise removal and gamma and binarization, which will help improve the results. So after that, just for us to understand the proof of concept, to believe that our OCR model is performing good, the team collected a list of Berlin and Munich bus details and performed post-processing to get the correct information. And this is to just validate the results that our pre-OCR model has got. Next comes our modeling of the empty seat. Over here, the aim is to understand if the user, if an empty seat is present in real time, again with good precision. Except the detection of the bus number and the bus name, both of the other models have to be detected in real time with good precision. And it again analyzes the input from Travis and finds the empty seats. And for this, our model architecture was MobileNet v2. In any of the cases over here, we did not use ResNet or we did not use DenseNet because of the low computational power of the mobile devices. And Travis is to be embedded within the mobile for users to use. A few challenges and further improvements that we actually want to do in the bus seat detection or empty seat. It's always about data. Without data, it's always very difficult to build a model with a good precision or good accuracy. So it is definitely important for us to get meaningful data with more, and the way that we get meaningful data, the best way that we collected here was how collaborators went on by themselves to collect data. But we also have to build other methods to actually collect the meaningful data. And the training versus deployment, because most of our training, a model cannot be trained without any GPU. So we actually use GPUs to train them, but at the end we had to deploy it on a mobile device. And one other challenges were that we had to correct on the extracted text to post-processing. For OCR itself, we performed 3 steps. There was a pre-processing, we used the OCR model to detect the text, and then we had post-processing. So via post-processing, we were able to validate if the bus is actually going to Berlin or it's actually going to Munich, and there were various reasons around it. So we had to a bit work upon our OCR specific one, and also creating language specific models. This was kept in mind of only the German language, but it is also necessary for us to extend it to the other languages. Such a pipeline or such a flexibility has to be built. And a few suggestions on the improvement is that, again, adding negatives, as we discussed in the previous data labeling improvements, because right now we only have a lot of buses that are actually incoming. So it's also necessary to create an unbiased model by adding a lot of negatives. And we also have to make use of augmentations so that we could get more data, and a more depth analysis can be required with, and also the Travis device, of course. In this, we built a model so that Travis, which was built by Renew Census, can be used. But we also laid an emphasis that we can work more on the Android app. And this is our mobile testing approach. So we know that we deployed it on the mobiles. So we had to evaluate the performance on that. That's the only reason that we actually used YOLOv for tiny and mobile net SSD models. These are a few architecture as to how we deployed it on the mobile device. We tested on a variety of mobile phones with a variety of hardware. And the main point to note over here is that our fellow collaborators from Germany actually tested it on actual German buses, which is like the main point over here to be noticed. This is our mobile app. As we can see, this is the TensorFlow, this is the Travis module that we have, and we can see that the bus panel is being detected with so-and-so accuracy, and then it detects the object detection of empty seats happens over here. Our deployment was quite simple with taking AWS, Amazon Web Services, and a Docker container, where we managed to retrieve all the data from AWS. And we also trained the model using AWS. And finally, the models were deployed at Docker containers, after which it was given for Android mobile testing and deployment. This is a quick ML flow pipeline. Maybe we can refer it for like the later on, or I can confirm in like any doubts that you might have. But this is a quick pipeline or a representation of what I actually was talking for quite a long time, from the data set to validation testing, buzz detection, how we actually work along with Travis. I do have a very short demo that I would like to show as to how the buzz detection was happening. The first case we had, if the bus is incoming, and then that was detected, and then it detects the bus panel. And a few things that we do consider as future work is that backside of the buses were wrongly detected at the front side. So that's also an addition to the data set that we have to include, because the backside of the buses were never included. We also tried to check with OCR Chinese models, and here we go with how we had the empty seats that were detected, as we can see in the video. Yes. So this is about the demo. And before I actually end the presentation, this is our summary on the possible next steps, that we would like to work more on German data, location-based data, because these only Berlin and Munich were considered. We'd also like to extend it to the other cities of Germany. And we'll have to perform more testers on Travis and take care of the model deployment. And as I mentioned over here, this is our huge set of collaborators, where we have like 40 to 50 collaborators from all around the world, representing about 12 to 13 countries who took part in this project. It definitely wouldn't have possible without all our collaborators helping dataset collection, dataset validation, etc. So I would like to end this by actually saying a thank you to all those who helped here. These are our Omdena collaborators who have various levels of experience, from being a data labeler to a technical mentor.
Thanks, Harini, for the insights. Really, really interesting project. Also well presented. I already noted down some questions, but I would leave for the audience first the opportunity and possibility to ask some questions. I'm sure there are some, so feel free to either just unmute yourself and ask questions or write it in the chat as you feel comfortable. Yes, Ben.
Yes, hello. Thanks for the nice talk, of course. One question that I want to ask is, you mentioned that you want to extend your models to other locations, or other cities, for example, or even other countries. And I was wondering how you would do that, and specifically if you would use all of the data you collected from different countries for a specific country, or if you would, for example, use all of the data to train a model and then fine-tune maybe on data that you collected for a specific location.
Yes, thank you very much. This is a very nice question, because we were also like this was kind of challenging. And at the end of the day, we definitely don't want the model to be working on only one of the locations and not on any other locations. So we wanted to build a generalized pipeline, and the main issue with actually making it global was there are different kind of buses in different regions. In Europe, the buses look different, and the US, the buses look different. So we wanted to focus on two main things to build a generalized pipeline. That is to collect all the images of the buses from different locations and to train on that if a bus is incoming or not. And it's also about the OCR, where first we have to recognize what is the language that is being used there. And once we recognize the language, then it's about the data set, our database. I would say once the language is being detected, that if it's Chinese or if it's English or if it's German, and after that we need to look into the database to understand which city that belongs to, because that OCR is a two-step process. So we will need to have a huge data set collection of in every city the bus number pertains to which location, and we will have to like pick up from that. For that, again, we will need to detect what language is that, and then follow up.
Then maybe I would add on this. So what do you think is then the more efficient approach? Because you mentioned also that the resources are pretty scarce on the mobile devices and on a Travis device. So would you also think of having different kinds of apps, so to speak, for different countries, or would that be like one global app that could be used in any country?
That probably I think Renew Census would be actually doing it, but I think as far as they wanted, it's one global app for the entire that's entire world. So that should be it. But again, the resources are very sparse, as in because we have to deploy it on the mobile and we do not have that much computational power. But again, we'll train it extensively on the AWS containers and the SageMakers, after which we will actually deploy it on the mobile device. So every time that we want to do the training with addition of new images, we want to pass it onto the virtual machine where we do the training. And then with those results, we embed them into the mobile device.
Very interesting. And did you also do tests with the Travis device at all? Because I think that, yes. And the demos you showed, they were with mobile apps, right?
That is a Travis. Yes, so Travis is actually a device that we fitted into our eyes, which actually captures the incoming bus, and then that is sent to the app, the mobile app, and the mobile app predicts. So Travis is a device which is built by Renew Census. So that's how our collaborators from Germany actually went ahead, and they do not have the Travis device in hand, but they were able to capture using their camera what the bus incoming, and they tested on the app that was built.
Okay, got it. Very interesting approach. Any further questions from the audience? Yes, Alexander, maybe next.
So I think I didn't completely get how you classified the chairs in the bus. So you said you got demo videos from YouTube, but how you tell your program what is one seat or what are two seats nearby, because both seats are blue and there's no strict line between them.
Yeah, so what we did that we collected a lot of images from YouTube videos. We generated images from that, and we annotated. Again, we used CVAT, where we annotated separate seats. So all the collaborators actually used a set of rules as how we can annotate. So with major difference as to like what actually splits two seats in between, we kept that in mind and annotated a few buses. After annotations, when we get the labels, we trained our model on top of that. So that's how we built the empty seat detection model.
Okay, thanks.
I wanted to ask if there is already, but I don't know if it's part of then another project maybe, but when you have the seat detection, how you would tell the user where a seat is. So because I guess they would want to sit in an empty seat, and how you would probably direct the person to the empty seat after you detect it.
Yes, so this is something that the Travis device, the Renew Census team take care of it, because they built the entire system to make it compatible with visually impaired people. So they have a mechanism which actually tells them the direction of the empty seat. So we provide with the coordinates of where the empty seat actually is, and it's on them as to how they show the way. It could be actually, I think they were using generalized maps, but because within when the area is too small, maps wouldn't work that good. So they have their own mechanism as to how they can actually show things.
Okay.
I have a few more questions. So one would be like, in terms of time, you said it's 8 weeks in total. How long did you actually take to on the data collecting part, and then on the actual training and like testing stuff, or was that all in parallel? Maybe you can elaborate a little bit on this.
Yeah, so most of all our projects happen in parallel. So we have various tasks with a lot of collaborators working on different tasks. So we wouldn't wait, it wouldn't be pipelined as to we wait for task one's result and then integrate with task two results. No, it would go on in parallel. So we'll have like toy model, at least if when we didn't have the data, we at least had a toy model which was up and running. So all the tasks would happen in parallel, only then we'll be able to complete in like 8 weeks time. And it's our team of collaborators, of course, who are able to do this.
Yeah, I find this personally really impressive that it's only 8 weeks, and if I'm informed correctly, then usually your teams are between like 20, 30, 40 people working together.
Yes.
And so it's impressive that you don't lose any like friction energy between all the collaborating contributors that are involved.
Yeah, most importantly, because they're from different countries, like from Eastern Asia to the to North America, our time zones are very disrupted, but still collaborators were able to make it up.
And how did you actually get the German collaborators? How do you reach out to them? Is there any kind of community platform or?
Yeah, so we are a global community by ourselves. So we have collaborators from all over the world who apply for our projects. So we have collaborators from North America, from Asia, from Europe, from Middle East. We have collaborators from everywhere.
So if people from our community would like to do some of those cool projects, then you would just register on your Omdena platform, and then.
Yes. So they will have to apply to our projects from the website, and yeah, that is all. Then we will be able to like invite them. They can. We have a lot of other things other than just the projects. It's also about it's also other than the projects. It's also about the Omdena school, where we have a lot of practitioners from our own community teaching few courses, teaching few topics, so they can get access to that. And we have local chapters in every area. So yeah, we have a lot of ways that they can actually participate with us. And the best way is to apply for a project.
Cool. Any
so
further?
Yeah, this is our link, which just has an Airtable link where we have to be like apply, and then our community team will get back to you all.
Cool. One more question would be, like, how do the challenges come to you guys? Like, can you just, like, if we, for example, have a nice problem somewhere here in the surroundings, then we can just submit it, or how does this process work?
Yeah, so again, that's the way that you'll get in touch with our sales team.
All right.
And you can just directly contact them and they'll take care of it. That is, so we have work with us for organizations as well. So we call this innovation challenge. We have a lot of challenges in this. If you want like a pre-vetted team, a remote engineering type of team, we have that. If we want like an AI innovative challenge, we want that. So all you have to do is just like request a demo, and then our sales team will get in touch.
Cool. Then maybe the last question from my side is you mentioned that you focus on a data-centric approach, and I know that this term by Andrew Ng is like quite recent a little bit. So what does it mean for you, like the data-centric approach, and can you maybe say a few words why and how you approached it in a data-centric way?
I mean, this was approached in a data-centric way primarily because the data was very insufficient, or we wanted to lay more emphasis on the data. So some projects need more technical involvement and some need more data involvement. In this, we believe that it needs more data involvement because the data sets are not easily available in the internet. And we wanted to follow a data-centric approach just to ensure that our accuracy and validity is the same. Because if it was any other case, that if we were building it for any other purpose, a few here and there on accuracy is fine. But when we're actually building it for people who want to use the bus for their daily uses and all that, I think we have to get a very good accuracy. That's why we intend the data-centric.
Yeah, true that you need high accuracy in that cases, and also really impressive that it's real time. I mean, it's also like tiny devices, real time, still high accuracy. So cool approach. I came across one more question, like how does this project now go on? Do you hand over the solutions to the renewable sensors and then they are in charge?
Yes, so we hand over all the solutions to them, and then they take it forward, because Travis is their device and we do the project for them. So
interesting. Harini, thanks a lot for taking the time and for presenting. That was
thank you very much from my side for having me here today.